everyone. Welcome to the course of Fundamentals of Micro and Nanofabrication. So we will be discussing here the week 4 of the course, and I am Udit, PMRF scholar from IIT Madras. So uh, coming to the course, so here the course this week basically uh, dealt with the basics of the CVD. The first video was on basics of the CVD. So the second was on precursor transport in CVD systems. Uh, then we go on with the practical aspects of CVD, the equipment and how they are controlled. And then we go with the theory of nucleation and growth and how to control them. And the last video is on the other details like the other types of CVD and other controls which can be used for getting a thin film using CVD systems. So this is the first question that says that this is the reaction which we need to uh, fulfill. So SiCl4 plus 2H2 gives silicon, elemental silicon plus dash. So you have to fill this dash. So this is a special type of reaction in CVD. So anybody has any clues? Like, we have different types of reactions. So this is what we call as a reduction type of reaction. Like we have different types of pyrolysis reduction, deprotonation, and oxidation. So a lot of reactions are there. And out of this is the reduction type. So here the thing is, SiCl4 is converted to silicon. So hydrogen and silicon come together to form this halides. And to balance it, we have to add like 4. So this halides, so this is what is goes on to say. So these halides are very uh, this is a very prominent technique that is used, but these halides are very dangerous. So this limits its use sometimes because we need a very uh, uh, proper system for releasing such things because and also the CVT system should be designed such that these halides are not released as it is, and we treat them before freezing because these are very dangerous. So this is what it is. So the problem too is we talk about two regimes, the surface reaction rate limited, the reaction rate limited, and the other is the mass transfer. So here for reaction rate limited, should the following things are correct. So it is a multiple type question. So that is the answer. So you all can write the answers in the chat box. We will take it up from there. Okay, so okay, let's go to the answer. For reaction rate limited conditions, usually like we can define such conditions with the Arrhenius form, like K equal to K naught e to the power activation energy by KT. So here uh, it is very much sensitive to the temperature. So that's that. And regarding the flow dynamics, like it is not like for flow dynamics, it is usually the cases where it is the mass transport is there. So there mostly the flow dynamics play a role. So in a sense, the reaction kinetics it has not much of a role. So this is not out of question. So temperature dependence is there, and we need to know that in both the regimes, sensitivity to partial pressure is there. Like partial pressure determines has a huge role in both the regimes. So uh, C is also a correct option. Let's go to the third question. I hope it is clear. Yeah. So which of the following is true for cold walled reactor compared to the hot walled reactor? So you need to select the right options for a cold walled reactor for a civil system. So these are the options, and these are multi-correct. So, many factors can be a part of the cold walled reactor. So you all can try. We will wait till everyone tries. So you all can start writing the options whichever you feel is correct. So then you can take it up. We will discuss each and every options. Separately. So anyway, what is it? Okay. Uh, so the thing is, with a cold wall reactor, so only the receptor inside the chamber, like in the chamber, only the receptor that holds the uh, substrate is heated. While in water reactor, the whole chamber is heated. So the first question, first option is fast temperature. So you can see that in cold wall, only the receptor is heated. Okay. Uh, so here we can see that, and in this, the whole chamber is heated. So this temperature ramping, so we need to control only the temperature in the receptor in a cold wall, while in this, the whole thing in a hot wall. So when we are controlling only the temperature of the receptor, the more control is on us. We can increase its temperature, we can decrease its temperature, and it will go like we can do it most more swiftly because the uh, like the things involved is less here. Uh, so temperature rise, ramping temperature is favorable here. So the second option is low thermal mass. So thermal mass is something that involves how much of the system, how much part of the system is being heated, thermally active, thermally active. So uh, here in the cold wall reactor, only the receptor is the thermal mass here. while in the hot world reactor, the whole chamber is the thermal mass that like loads the heating system. So the thermal mass is there is low. So B is also right off. Temperature non-uniform. So in cold world, what happens is that the other areas involved are cold. So the receptor is heated. So there is a chance that this like it happens that as the receptor is heated, it loses its heat by radiation to its walls. So maintaining temperature is somewhat hard here. So yeah, it can give rise to some temperature non-uniformity. And okay, so some of you have told like correctly about some of the options are correct as told by you. So the fourth option is gas phase nucleation. It means that it nucleates the precursors nucleate at the form nucleus like form starts forming nuclei which is like coming up of some of the atoms come together, form a nuclei, and it goes to form like a nanoparticle. So, nanomaterial. So, gas-phase nucleation is very hard to happen here because as the chamber is like in the chamber, only the receptor is heated. So, the gas is not heated. So, for that, like energy is required for nucleation. So that energy is not achievable in a gas phase. It's only achievable in the uh, like on the substrate. So gas phase nucleation is not possible. Low precursor consumptions. In a cold world, only the receptor is something that involves nucleation. Now, all the materials, all the precursors comes and sit together and have a chemical reaction. While in hot world, whole chamber can are sites of these reactions. So precursor usually is consumed more in whole chamber, while in cold world it is very confined. The reaction area is very confined. So most of the reaction happens in the susceptor. So as a result, a very low precursor is consumed. The next is low deposition rates. So deposition rates here is comparatively high because it is very confined, the same reason. So this is not correct and ideal for LPCVD. So here we see that this option, temperature non-uniformity. For LPCVD systems, we need to have the temperature uniform because it mostly has a higher dependence on the temperature because most of the because more high probability will be there that it will be running in the reaction dependent extremely limited regime. So it is not ideal for the LPCVD system. Clear, clear to you all. Okay, so the next, if any doubts, you can ask. Otherwise, we'll go to the next. So this is problem 4. So an APCVD system is designed to run in mass flow rate limited regime, which was programmed by a student to run at lower temperature, having the same precursor uh, pressure and temperature. Substrate is heated by circular heating coil, causing 5% temperature non-uniformity across the diameter. Okay. The normalized growth rates for both the cases, like case A and case B, uh, is given. What we have to tell which case does B correspond. So you all can write the answer in the chat, then there will be further discussion. Okay, so let's go to the solution. So we can see that in the B condition, this is the normalized graph. So with temperature, like this is the this red line is the temperature. There is some change with the temperature, while in A it's not there. So we know that mass transport limited regime is like in APCVD, it is insensitive to the temperature changes. So, but while in LPCVD, it is the changes, the temperature variation is there. So due to the temperature variation, we can say that this is a low pressure CVD system and not a APCVD system. So fully described. It is except like clear to you all. Then you can go on to the next part. So this is a true and false question. This is a statement for faster and thicker depositions. APCVD is more preferred over LPCVD systems. So true or false? Have to write the chart. So whatever you feel, the answer is can write down. We'll take it up. So APCVD system is something. which is atmospheric, and this is one pressure. So atmospheric fluid and that is flow fluid. So you have to tell in which of the following systems quicker or faster deposition is more favorable. Okay. So we know that in APCVD systems, we tend to work around atmospheric or more than atmospheric temperatures. And in LPCVD, the pressure is quite low. We have to establish a like vacuum also to go to LPCVD system. So, and we know that when the pressure is higher, the growth is also higher. Like uh, pressure, sorry, pressure is directly proportional to the growth. So as it is high pressure, we get that we tend to get quicker depositions on the substrate. So the answer is really true here. So thicker films are formed, and as the pressure is higher, the materials are also uh, like transported very instantly to the very prominently to the substrate. So this is the problem 6. So this is a multiple correct question, and we have to tell which of the following factors are true for a PCVD system compared to the LPCVD system. So we have to tell this is true for LPCVD. So 6 factors are there, and we have to tell how they differ from the LPCVD. So, okay. So, so, so here we see that the first option, that is sensitivity to temperature uniformity. So, in APCVD systems, the systems are APCVD is mostly like they are dependent on uh, reaction rate. So, uh, because as the pressure is higher, diffusion is not an issue here. So, sensitivity to temperature uniformity is not here. So it is a reaction rate limited. Uh, the second is axial stacking of wafers. So axial stacking means that in the chamber, there is this inlet, outlet, we're stacking it like this. So in axial stacking is not ideal for APCVD systems, and it is mostly seen in LPCVD systems, and that's why mostly APCVD systems is you can't scale it up, but in LPCVD you can scale it up. This is because uh, the temperature relevance is not there, but uh, this is most of the thing is it is this flow pressure depending on the this is, it is APCVD system is mass transport limited. So uh, it is not reaction like temperature with the like reaction rate limited. So temperature uniformity is not there, but pressure uniform like depending on the pressure, there is changes. So as if you place the axial systems like axially, there is a chance of like forming a stagnant layer here. So pressure from this bulk will be different from this pressure. So this can give rise to like a differential like uh, not a proper substrate film. So that's why axial stacking of wafer is not possible. It's not favorable. Uh, the thing is precursor consumption. Uh, yes, because the because high precursor consumption is there because these APCVD systems tend to grow thicker films because of this uh, because it usually happens in this cold world reactors. Uh, this FPGA systems have higher consumption. Plus, it has high pressure, so the precursors tends to sit on the substrate easily. So, high precursor consumptions are seen compared to the FPGA. High precursor concentration. So, in APCVD systems, we tend to go for lower concentrations compared to LPCVD systems because in LPCVD system we are getting low pressure, so we tend to have high precursor such that it can negate the effect of lower pressure. So here lower concentrations are also possible and favorable. So and the last thing is mass transport limited. So it is mass transport limited. So uh, C and E will be the correct options. So problem 7. Uh, so this is a statement that supersaturation occurs at partial pressure equal to equilibrium pressure. True or false? So the alternative. So supersaturation event is a very important for nucleation to happen. So You can write whether it's true or false in the chat box. Okay. Uh, so let's discuss the answer. So this is something I picked up from the PPT, from the video lecture of the course. So here we see that the partial pressure, where it is equal to equilibrium pressure, the rate of adsorption and the rate of desorption is quite equal. So whatever the precursors are absorbing, they also tend to desorb also. So it goes on like this. So this goes on where it is absorbed and also dissolved at the same rate. So effectively, very less part is getting deposited. While when the partial pressure is high, uh, the absorption is higher than the desorption. So uh, more particles are deposited. So this is the case of supersaturation. So it is false. So we tend to give more partial pressure so that more particles are present on the surface, and it can, like, chemical reactions can happen in the surface. So this is the case. Otherwise, if it would be dissolved, otherwise, if the pressure is in equilibrium, it tends to get dissolved to the bulk medium. So this problem 8. Uh, so in the case of no weighting, so no weighting is this one. The contact angle is theta equal to 180 degree. Following conditions are found to be true. So this is a multi-correct question. So you can try. Let's go to the solution. So here we can see that uh, in this we see that uh, when this these have this they nuclei form like this hemispheres in the surface, and when they grow, like when they grow on all the sides and form a thick film, they like collide with each other and form such kind of boundaries. And usually these boundaries like this, when they are growing, they don't know about like the crystal information about, they don't have the crystal information of this, and the spheres are not same. So usually they try to grow like independently, and when they collide, these crystal domains are different, and so it is not very desirable for epitaxy. So epitaxy is a single crystal structure on a similar crystal lattice. So it is not very desirable. Nuclei grows more in height, so it is a kind of a 3D growth. So it grows like like a hemisphere. So not in area. So aerial growth, like it is not spread out growth. So this is correct. It is seen in heteroepitaxy conditions. So like germanium on silicon in such conditions, these are very seen, and also we can see some uh, like heteroepitaxy conditions here also. So that's correct. And when it like when the 100% coverage is there, it forms a thick films, because these are like growing like a radially growing, they form a thick film on 100% coverage. So that's the thing. So it's question number 9. So we discussed that for a lower nucleation rate, which of the following is desired? Low temperature, low partial pressure, high partial pressure. So different factors are here: temperature, partial pressure. So you have to see the dependency. So this is a single correct question, so you can try. Only one option out of this is correct. So coming to the answer, uh, so here we have to get lower nucleation rate. Uh, so the first is low temperature. So like taking example of water, when we need to nucleate it, like we need to get a like conversion of water to ice, where it forms a nucleation, like it forms nucleus and then the crystals form. So in that process, we have to lower the temperature. So but here, so basically we can say that nucleation, like for a nucleation to happen, we need lowering the temperature from melting, from its beyond its melting point. Uh, so we can see that if we increase the temperature, so it should lead to lower nucleation rate. So low temperature would be favoring nucleation. So this is not good. The second option is partial pressure and high pressure. So this we can talk together only. From our last question, we saw that this rate of uh, absorption in and a rate of desorption. It increases in the condition of high partial pressure compared to equilibrium pressure. So uh, for lower, so this condition gives rise to a supersaturation, and supersaturation is something that favors nucleation. So for uh, lowering the nucleation rate, we need to go reverse. So if high partial pressure is giving rise to more supersaturation, the lower partial pressure would be very favorable for getting a lower nucleation rate. So this is the answer. So this is the last question. It also deals with nucleation. So we have two statements, and out of this, one is correct. So you have to tell which one of them is the favorable one. So here we are talking about two types of nucleation, homogeneous and heterogeneous. So homogeneous is something that happens in one phase, and heterogeneous something that happens in between two phases. So that's the thing. So you all can try. Okay, let's discuss it. So this thing is more clear. This is something I took it from the slide where it deals with the contact angle of the. So from the contact angle, we see that the delta G that is there, the delta G for heterogeneous is less than the homogeneous condition, because this is something that comes to be negative. This is something that comes to be yeah, like less than one. So uh, and also negative. Uh, so this gives rise to that the heterogeneous is less than this homogeneous. So the probability is delta G is something that whichever is more negative is more favorable. So heterogeneous nucleation is more favorable than the homogeneous nucleation. So this is correct. And regarding homogeneous nucleation more favorable CVD, so we can see this condition like if we have homogeneous, like in the gaseous phase, this is the gaseous phase, and this is the substrate, and where it is the heterogeneous phase. So if nucleation happens here, So we will get clusters of silicon which will rain down on the substrate, and it will get like this. So this is not a favorable condition, as we want a thin film on the surface, not like dots, not like clusters of silicas here and there. So this is not a favorable condition. So homogeneous reactor nucleation is not favorable for CVD for getting a thin film detection. So that's all for today. Thank you all for joining. If anybody has any doubts, they can stay back. Others are free to leave. Thanks a lot, and we will meet in the next time discussing the week 5 problems and doubts. So thanks a lot, and hopefully we will meet